So I guess before anybody comes in, if at all, do you have any specific questions?
Not really. I was just well, we have the exam next week, and so I was just going through the sample questions that they give.
Yeah. This is like 4 or 5 questions.
Yeah, five questions.
Yeah, we can. If you want to look at that instead of talking about second order differential equations, it's fine.
Yeah, I was trying to solve some of them, and I got stuck, I think, on the fourth one.
All right. So you said number 4.
3 and 5. I got 4, but 3 and 5.
Oh, that looks rough. But maybe so. You know how to kind of go through the checklist? You've seen our flow chart?
Yeah, actually.
Okay. So I'm not sure what this is, but to me, I would try to see if it's exact. It's definitely not linear, right? Because you have y cubed in there, y to the 4th.
Yeah.
So maybe we can rewrite this as
That was some form of Bernoulli's. So.
could be Bernoulli, except that we have a y to the 4 and a y cubed. So I'm not sure about that. Definitely doesn't feel exact. I mean, homogenous. But y prime we know we can write as dy dx. So we're just going to rewrite it in differential form and see if maybe some sort of, it's probably not exact, but maybe there's an easy integrating factor.
Right.
So we're multiplying through by dx, so to speak. I mean, what did you try?
I was stumped. I didn't know what to try, really. I brought it so that dy by dx was equal to 5y minus 4, y to the power 4 over that whole part, making that the denominator. But I did not think of it this way.
Yeah, so there's 2 different kind of flavors of how to present these, right? There's the y prime is equal to some function of x and y. And then depending on what this looks like, you do different things. Right? If you have some sort of combination of a function of some sort of combination of x and y, then that suggests that we should just lump this into a new variable. Or you might have, well, they're not equal, but you might have like a function of y over x, so it's homogeneous, and so on. Okay.
I think my problem is that I know how to do the maths aspect of it, like the actual calculus.
Yeah.
When I'm given a question and I'm told like this is the method you can use, but identifying the method is the tougher part.
Yeah, I definitely see a mess. I don't know what to do, but I do know not homogeneous because the combined power, the degree is not the same. It's not Bernoulli because we have different powers of y.
Right.
Anyway, it's multiplying y prime, so that doesn't make sense either.
Right.
Yeah, so I'm just going to try to write it in differential form.
Okay.
And then look for exactness and integrating factor. So we identify the m as the function multiplying dx. Okay. And so we're going to check for exactness. So differentiate m with respect to y, differentiate n with respect to x, right? But that's very close, and it's suggestive, right? Because it looks like we only have y's involved, so it's very likely you can probably find an integrating factor that's just a function of y.
Right.
And what's the test for that, if you want to remind me? I don't want to memorize it. So if we guess that we have a function, our integrating factor is just a function of y, what has to be true according to the flow chart?
As in, like what this is supposed to equal?
No, no, not what it's supposed to equal, but when we look for integrating factor, in general, it's not easy to find one, right? And it's not unique. So what we try to do is make some simplifying assumptions, like the integrating factor is just a function of y.
Oh, right.
It's just a function of x.
Yeah, so this should only involve y, because we're
Yeah.
integrating.
And what's the official kind of check whether our assumption is correct? So nx
Yeah, it's not one, right?
divided by n, right? So for our integrating factor to be indeed a function of y, we can check this necessary condition. And this has to be a function of y only. So we have the derivative of n with respect to x minus the derivative of n with respect to y, all divided by n. So indeed, okay. So this would reduce to 3y squared divided by y cubed minus 5.
Right.
Okay. So that checks. So this is just a function of y. So now we know that our integrating factor is going to take the form of exponential of an antiderivative of exactly that expression. Okay. So this is not one note.
So can you do this check in any direction? Like you can check for if it's a function of only x, or if it's a function of only y first. Doesn't matter, right?
Yeah, whatever seems like, you get a feel for it, but you can just try both.
Got it.
And it's kind of like you got to know your professor's mind, or what, because your professor, some professors would say, well, you should know how to derive these formulas, these checks, on these assumptions. Is it a function of y? Is it a function of x? But some professors will say, well, here's an integrating factor that's a function of x times y.
Right.
And then you have to know how to rederive the formula for the integrating factor. Let me just make this person a moderator. Okay. All right, so we do this integral, and it's clearly log of up to a constant, but we're just looking for some integrating factor, so let's just even forget about the absolute value bars. So apparently, that's the integrating factor, which looks terrible, absolutely terrible. But what's the purpose of the integrating factor?
So that you make the equation exact.
So it's not exact, but after multiplying by the integrating factor, it's designed to make this exact. So let's go ahead and try that. Okay, here's the original, written in differential form. Here's our integrating factor, apparently. So we just multiply the original by this. And whether we want to use a product rule multiplied through, I guess that's up to us. Doesn't seem too pleasant, but okay. Oh yeah, by that. Sorry. Well, let's just, before we go on and waste our time, let's just double check. That this is indeed exact. So we might call this our new m, or if you'd like, n tilde or something. So let's differentiate it with respect to y. So I'll just use the product rule. Well, that's a mess. Okay. And then our n, our new n, you might as well call it n tilde. Differentiate with respect to x. So you get okay. 6. Let's demonstrate something. Ah, there you go. Sorry, there's an x here. So we're going to get yes. Can you want to use chat? You can't see the projector. Okay, thank you. That okay? There you go. You should see it now. Okay, so now you can just can we factor anything? Yeah, let's just multiply this through. Okay, so we get over here. Okay, so how many y to the 6's do we have? 3 and 7. Okay. And then how many y cubes? Negative 15, negative 20, negative 40 of them. Indeed. And then we have a constant. So they're equal.
Right.
Okay.
Okay, so now they're exact.
Yeah, and so do you know how to, so what, we're trying to recover a solution in what form?
In the
So it's like the solution is the form of a function, if you will, or an equation. We call this maybe a level set solution because we have a function that's equal to a constant.
right.
Constant is based on some initial condition. Or maybe an integral curve it's also called. So.
Right.
Okay. So we know that the idea is that if this is the solution equation, if you will, or solution curve, then if you compute the total differential by taking partial derivatives and multiplying by the corresponding differential, that's equal to 0, we see that this should be n tilde, and the derivative of psi with respect to y should be n tilde.
So you integrate either of them.
Yeah, so it's your choice.
Right.
What do you want to, if you want to get phi, or psi, sorry, we would anti-differentiate, say, let's take psi with respect to x. We anti-differentiate that with respect to x to get rid of that partial derivative. But psi with respect to x is exactly n tilde. And that was pretty simple to anti-differentiate. I'm going to take the multiply, well, yeah, I'll just leave it as is. N tilde. So this gives us x times this business, and instead of a constant of integration, what do we get?
Oh, you have like some. Well, we use h of y, or you use any.
Yeah. So some function of the variable
Y.
y, right? And we know this is correct because if you differentiate this with respect to x to undo the antiderivative, you would the h of y would go away because there's no x there.
Right.
Beautiful. All right. And so what do we do next? We have psi, except we don't know it completely because we don't know what this h of y is. So how do we find h of y?
Well, there are two ways. One, you can integrate n,
True. Very good.
right? Or you can, well, you have to integrate the n to find
Yeah.
this, or you can differentiate this function with respect to y, which is a little hard for me, I guess.
I don't know, because I don't want to, you have to anti-differentiate n tilde with respect to y. I'm just going to differentiate psi here with respect to y.
Right.
And we know that's going to have to equal to n tilde. So, which I kind of already did that, right? When checking here.
Yeah.
And then here we can write h prime because it's a function of just one variable, so we know exactly what the prime refers to. And we would set that equal to n tilde. Okay. Is there space here? So we'll come back to number 4. Where are you, n tilde?
It's a little further on, yeah.
Yeah. Really, to test your knowledge, they gave you this kind of unnecessarily thing that's like annoying and laborious to.
You don't have to open it up.
Yeah.
Okay.
But I have a feeling if we do everything right, because these are equal, anything that has is a function of x should go away.
Mm-hmm.
Because we should just be left with h prime of y equals some function of y.
Right.
Otherwise, we have a contradiction. So, I mean, that's a shortcut, if you will, but not.
So in that sense, you can just kind of disregard any terms that involve x.
Yeah. But that's assuming you feel comfortable with what you just did. Like, I always like to check anyway,
Right.
make sure, but.
I mean, I did open up the brackets.
Let's just factor out an x here, and yeah, so you get. I think I also already did that. So let's see. So we said 7 of these. Negative 15, negative 20, negative 40. Yeah, so I got previously 25. And then multiplying out n tilde. Right, you can probably gather these terms, factor out an x. And we get 7 y to the 6.
Minus 40 y cubed again.
Yeah. And then we'd be left with a 25. But what I didn't foil through with is that y. So that would be y to the 4th minus 5y. So indeed, these are equal. As we anticipate, if we're doing things correctly, functions of x just cancel out when we equate these two.
Right.
And now we see that h prime if I okay, wrong thing. H prime. So this is as simple as it gets. See, we did this in calculus 1 without calling it a differential equation. We just get rid of the prime, deprime the sucker by integrating or anti-differentiating. Okay. So there we go. We can now finally update our psi function.
Right.
And apparently it's equal to the business. So I'll write it as x times this polynomial in y plus, oops, no. Where is psi? Oh, it's right there. Nothing revolutionary here. And where we can, now we know what h of y is. Yeah, I hope they don't do something like that on a test. I mean, that's a, it's like a landmine for simple mistakes, you know?
Yeah, the way that they gave the question kind of threw me off, and so.
Yeah.
Okay, this makes sense.
Well, that's part of the trick, you know, for first order differential. Like you have to kind of recognize, start manipulating until you recognize one of the standard types. All right, so did you say you want to do number 4 as well?
No, I think I got number 4, but I might want to check that answer because they're not going to give the solutions till the end of the week.
So that's definitely what type? What's the type here? I'm going to go ahead and erase this. What's the giveaway, I guess?
I just took it as homogenous.
Yeah.
Homogenous, and I did the substitution where, well, I used u over here, but you can use z is equal to y over x.
Yep. And so here, it's nonlinear because y is inside some transcendental fully. It's not getting just multiplied by a function of x. So we can maybe, once you recognize this is homogeneous, you can do the substitution right away. We could also maybe divide by x. So it's clear that it's homogeneous.
Right.
And assuming x is not 0. And if you get it in this form, you don't have to necessarily get it in the form y prime equals some function of y divided by x. Okay. If you see that it's homogeneous like that, then we can simply do the substitution where we lump this common expression into a new variable. And then maybe we want to look at it because we have to, you know, anytime you do a changed variable in differential equations, it involves derivatives.
Right.
So I'm going to rewrite this as y is equal to x times z. And when we say y prime, what are we differentiating with respect to?
With respect to x.
Yeah.
Right.
So yeah, we have to recognize always back of our minds what the independent variable is and which variables are considered the unknown functions. So here, y is the function, the unknown function of x.
Right.
And what about z?
That's also a function.
Sure, right? I mean, if y is a function of x, then y divided by x is another function of x.
Right.
So that's just my long-winded way of saying we have to use product rule because he's a function of x.
Right. Yeah.
Right. So we use product rule differentiating x times z plus x times the derivative of z. So z prime, if you will. Well, so this makes the substitution easy. And so y prime, is z plus xz prime minus z all multiplied by cosine of z plus 1. Now, if you've done enough of these, you know that if you have a homogeneous differential equation and you do that substitution, what kind of differential equation should you end up with?
Could you repeat your question?
So you have we have a homogeneous differential equation here. We did the standard change of variable for that case.
Right.
And we get a new differential equation, which is of what type?
Is it supposed to be first order?
Oh yeah, well definitely. Right, because you only involve the first derivative, but it should be like separable, right? I mean,
okay.
Invariably, like that's what you should expect, and that's what it should be if you're doing it right.
Right.
So, well, so how convenient, z minus z. So you get x cosine z times z prime plus 1, 0. So indeed it's separable. Is it?
Yeah, I'm on the right track. That's good.
Yeah, so we would move the 1 over, rewrite z prime as dz dx, so then,
Is equal to -1. Right.
and then there you go. We've all the z's on the left, all the x's to the right. Okay. So it's separable.
And once you integrate both sides, you'd have sine of c is equal to negative natural log of x, right? Plus c.
Okay.
And since they've given you x and y values, like they've given you the initial value, I think, in the question.
Yeah. So yeah. So right now we just have an equation that's relating, right?
Right.
So we could solve for the constant right now if you'd like. Well, I should say let's replace z with what we said is equal to. And you know, they might not want an explicit solution. I mean, I don't want to take like arc sine, because arc sine is not really a the inverse sine to the whole interval. So I'm not sure how that would work out. But we can just, unless they ask for an explicit solution, which they didn't.
They did give
An initial condition.
Yeah.
So y of 1 equals pi over 2.
Right. Okay. So that would just be sine pi over 2 is equal to c.
So, right, so when x is 1,
then natural log is 0.
Y is pi over 2. Okay, so we get sine of pi over 2, log 1. Okay, so we get 1 equals 0 plus c. C is 1. So then we can update our general solution, or we can say we can, out of this family of curves, we can pluck out the one that goes through this point.
Right.
So, yeah. Voila.
I think I used slightly different steps.
Yeah.
But I got to a separable equation. So I used u instead of c. Like I used this condition, but I just used u instead. Forgetting this. So it's a bit mixed up, but start over here. I separated, I distributed cosine, and then I brought it to so that dy by dx was equal to something like this.
Oh, so you wrote in that kind of standard form?
Right.
Yeah.
And then I did the substitution for this.
Yeah, yeah. I would have probably, yeah, if I were like in like just my first semester of differential equations, I would probably feel more safe if I wrote it in standard form first.
Right.
Because I'm not, yeah. All right.
I was just trying to bring it to the form that I saw over here in my notes as well for homogenous equations, and so that's why I did that. But yeah, this makes sense.
All right. Let's see if somebody in chat has a question. What else? I guess they left. Okay, well, that's not good. All right. So, do you want to talk about second order?
Yeah.
Right. Maybe since when did you hear the lecture about the constant coefficient business with second order?
I think we started. He introduced it last week, but then we actually did it. We have classes on Tuesdays and Thursdays, and so we did it yesterday.
Okay. So we have these special cases, right? It's simple but important. Second order differential equation. It's linear in y. It's homogeneous, so the right-hand side is 0. And we have constant coefficients.
Okay. Just to correct myself.
Yeah.
I think we started last week. Yeah. Written quite a few notes.
Oh.
Yeah. Started last week.
Okay. Yeah, I know that I did a review last week that involved second order, but not specifically the constant coefficient business.
Okay.
Okay. So, do you recall if you have constant coefficients, what you assume a solution might look like?
Well, you have 2y, so like y is equal to two different constants. So c1 is c1 y1 plus c2 y2. Does that make sense?
Right. So
if you have a fundamental pair of solutions,
right,
then the general solution would be y is equal to c1 y1.
This is true, but how do we find y1 and y2 for the constant coefficient case? Like, so for example, here's a differential equation, second order homogeneous, and we only have numbers multiplying y and its derivative, so constant coefficients. So the idea was to use this very special function. Have you taken linear algebra?
Yeah, I did it last semester.
Yeah. So think of this as an eigenfunction, like an eigenvector.
Okay.
Where this is a linear operator on y is equal to 0. And if we can show that if you have something in the form e to the number r times x, then this will be a eigenfunction in the sense that linear operator of that function gives you a multiple of that function.
Okay.
And we can just confirm that it works, right? So we're going to assume that we had solutions in this form. And then we would just differentiate once because we're going to plug it into as often as you notice in the pattern here is you assume some form will work, plug it into the differential equation, and you check what has to be true for it to work.
Right.
So we differentiate once, twice, where r is a number, and then plug it in to the differential equation. So a times y double prime, b times y prime, and then c times y. Okay. And indeed, right, e to the rx can be factored out, so you have a multiple of your function. So it's like an eigenvector, but eigenfunction instead. And can e to the rx be 0?
Right, 0.
No. So it can't. So we can just, this has to be 0, right?
Yeah.
Okay. So this is what do you recall what we call this? This corresponds to the differential equation where y double prime corresponds to r squared, y prime to r, and then y by itself, if you will, corresponds to r to the 0,
Right.
if you'd like that instead. But what do you call that polynomial? Well, it's just a name, so I guess it's not actually a, it's a trivial question, right? Or a trivia question, so it's a characteristic.
Oh, great.
But what isn't called a characteristic something or other in characteristic polynomial. So it's kind of like, for that differential, so it's kind of like a polynomial. When you find eigenvalues, you go matrix minus lambda times identity, and you get a compute the determinant, and you get a polynomial.
Right.
So that's very analogous, right?
Okay.
Okay, so we see that. So for example, here we're going to write down the corresponding characteristic polynomial for this differential equation, this specific example. And then we compute R. So we can use quadratic formula, or we can just, in this case, I believe we can factor.
Right.
So we see that R has to be either 3 or -2. Okay. So what is y1 and y2 then? Or what's the fundamental solution set here?
So over here, because they should be e to the power r1x. So y1 would be e to the power r1x, which is 3.
By the way, this is wrong. I was just supposed to say some multiple of that, but okay. Sorry about that. Yeah, so we assumed solutions in this form, so we can make y1 say e to the 3x, right? And then y2 is e to the -2x. Okay. So are these linearly independent? Like, we're finding eigenvectors and they need to be linearly independent, kind of.
Right.
So are these linearly independent?
Yes.
Well, prove it to me. What do you have to do to show that two functions are linearly independent on some interval?
Sorry, I'm blanking right now.
Okay, that's fine. So how do you, so if you have y1 and y2, and you want to show that you want to test whether they're linearly independent or not, you would create a combination.
Right, they can be.
And set them equal to 0.
Right.
Right, so this is exactly like linear algebra test for independence, right? But you have functions that are vectors. And then you try to solve for C1 and C2. And if the only solution is that these are 0, then we have linearly independent functions.
Right.
But, I mean, we're going to have to take derivatives here. Right, just take derivative of the left-hand side.
0. Yeah.
And then this becomes, you can express this as a matrix equation where the unknowns are C1 and C2. And here you have a matrix where the entries are, functions of the independent variable. So this is a function of x. But how do you know that C1 and C2 have to be 0? How do you know you get a unique solution of 0? If in linear algebra, what would have to be true about this matrix?
It's determinant. It has to be 0.
Non-zero.
Non-zero. Right.
So that way the matrix is invertible and you can multiply.
Right. Non-zero.
So to have independence here, we need these to be 0, so we need a unique solution. So this means that our matrix has to be invertible, meaning that the determinant is non-zero. And what do you call this determinant? For some reason, this gets somebody's name. Wronskian, right? So you want the Wronskian, y1 and y2, and in your notes, they emphasize that, you don't forget this is a function of x, should be non-zero on some interval. hopefully containing the initial condition if we have one.
Right.
Okay. So
They won't ever give an initial condition which is not on the interval, right?
yeah, so
Right now, please.
well, so it's going to be we have nice smooth functions. So you're going to get a continuous when you complete the determinant, you're going to get a continuous function. So it's going to be 0 possibly at some single points, not like intervals.
Right, right.
So they would have to choose a point that's not one of those.
Right.
And the interval you care about is just between the places where the Vronsky is 0.
Right.
That's the only place that the initial condition problem would be valid.
Okay.
Okay, so let's just double check, just as the good practice with Vronsky. Here's y1 and its derivative. Here's y2 and its derivative. Okay, so determinant. Oh no, it's negative. Is that bad?
No, it's just not a. It's a non. Well, since. Yeah, it can't be 0.
Yeah, that's all we care about.
Because, yeah, it's
Sorry.
anything is.
Yeah, I'm playing silly, trying to play silly mind games. But yeah, all we care about is that it's non-zero.
Yeah.
Anywhere. It's non-zero on the whole number line. On R, or negative infinity. So any initial value will work here. Okay. Yeah, so we have linearly independent solutions. And as you mentioned, then the solution, the general solution to the homogeneous equation is just a combination of y1 and y2. All right. So if we had an initial condition, let's say, so this is our general solution. So if we had an initial condition, would that be enough to solve for C1 and C2?
Because you have 2 constants which you need to.
You need 2 conditions.
Two conditions, right?
So the other one has to be, well, you could technically boundaries, right? So you could have y of 0 is 1 and y of, let's say, pi is equal to something else. But they'll typically just give you the derivative, right?
Right.
So let's say y prime equals 0. So once we have for our second order differential equation, 2 initial conditions, we can then get a system of equations going, right? But notice that it's going to be kind of like this, if that makes sense.
Right.
But the right-hand side is just going to be whatever this is, 1 and 0. But anyway, let's just go through it so it'll be clear. So we have x is 0 and y is 1. So, okay. And then we have oh, I have to differentiate. Sorry, excuse me. Y prime. And so now when x is 0, y is 0 as well. Y prime is 0, sorry. So you get and so then we solve this in any way we would like. If we don't like matrices, solve for one variable in first equation, plug into the second. I'll probably just write this as a matrix equation. Coefficients, unknowns, and that's equal to 1, 0. And this is invertible, so you can multiply both sides by the inverse. Do you remember the formula for the inverse of the 2 by 2 matrix or no?
No.
Okay.
Oh, wait, 1 over AD minus BC, and then you switch D.
Yeah, you
Switch
flip the
D,
diagonal
minus B
entries.
and C. Yeah.
And then what do you do to the B and C?
Minus B and C.
Yeah, you change the sign on the off diagonal. So this would be the inverse of this matrix. So what's the determinant? -5. Yeah. Which we could have guessed, but okay. And then we exchange the diagonal entries, change the sign on the off. I mean, I just so much. I just hate working the kind of high school way, solving these. Oops. Times the right hand side. So what do we get? -2 and -3. So apparently C1 is 2/5, C2 is 3/5. Okay. So our solution, the initial value problem, it's like a recipe, you know. Give me some of this function, some of that. Okay, beautiful. And that would be the solution. Okay.
So because we have two initial values, we're able to find C1 and C2.
Yeah. You definitely need two
Otherwise, we can
independent
just
equations.
write it in the general solution format, right? Like how you gave it initially.
What about it?
We can just leave it in that format if they don't give.
Oh, yeah, yeah. If you don't have initial conditions, then the best you could do is just get a general solution. They'll tell you, find a general solution, or they'll say instead, solve the initial value problem with these initial values. Then you know you're looking for numbers.
Right.
Okay. Now, I covered the simplest case for constant coefficients there, right? Because both coefficients were different, so we get two independent solutions, right? So what would happen if instead we had a characteristic polynomial with a repeated root? So, trick. It doesn't let me scroll down unless I put something down. Okay. So what if we had y double prime minus 8y prime plus 16y is 0, constant coefficients. Okay, and we again start assuming that our solutions look something like that, where we need to find r. So we write down the characteristic polynomial without rederiving the procedure. Now this is a perfect square, no?
Right.
Okay. So now we have that R1 is 4 and R2L is 4, right? It's like a repeated root, multiplicity 2. So if we were to write down the corresponding functions, we wouldn't have linear independence. I mean, so you have the Wronskian would be 0 everywhere.
Right.
So you would get, I mean, without doing any computations, right? The determinant of the matrix whose has repeated columns or rows must be 0.
0, right.
So that would be 0 everywhere. So, okay, well, that's a problem. So how do we find, we can keep one of these as a solution over our fundamental solution set, but how do we get the independent second function?
I know it's formed, but I don't remember how to get there.
Yeah, so they used, I don't know if we want to review it here, but they used something called reduction of order, right? What was reduction of order used for? So side note. Well, for second order differential equations, reduction of order says that if you know one solution, okay, so we have a second order differential equation, I'll write it in this standard form, where now P and Q don't have to be constants, right? And you're given one solution, given Y1. What we can do, because it works, again, an assumption that turns out to be fruitful, we can assume that Y2 looks like what? Exactly. So some unknown function, what do you want to, what do you like to call that function? Okay. Sure. All right, Z's good. So some function of the independent variable times the first solution. And again, if you wanted to rederive the formula, you just have to compute y prime and y double prime and so on. But what you would then get at the end of the day is a formula for z. So z is this function is going to be the antiderivative of a fraction. The denominator is the first known solution squared, and the numerator is e to the integral antiderivative of minus p dx. Okay. So that's the reduction of order formula. Okay, so once we know z, then of course we know y2. Okay. So to use this very quickly, if we assume that if this is not an independent solution, let's assume that y2 would look like some function times the first solution, right? And apparently the formula for this function that multiplies y1 is like so. So you get y1 squared and then we have e to the negative, and what's p?
It's -8.
-8. So, right, so unsurprisingly, we get e to the 8x on top, bottom. So that's just the antiderivative of dx, so we get 1. X. So it turns out that y2 is equal to z, which turned out just to be a very simple function of x times y1. And this procedure also guarantees a dependent solution, so we can check using the Vronsky. But now we have our fundamental solution set. And this always works, right? When you have a repeated root, just take the first exponential function and multiply it by x. Okay. And you can imagine higher order, you would do something similar. Right? You multiply it by x and then x squared. Okay. All right. So again, so we have the case where our characteristic polynomial had real distinct roots. And then we looked at the case where the characteristic polynomial has real but repeated roots. So you need to go, don't you?
Yeah, I have my shift starting in 4 minutes.
Oh, okay. You can go.
Okay.
We're going to need to cover. We'll cover the some other, I guess, the other cases, complex roots. Yeah, those.
Yeah, I think that we did that just last class.
Oh, okay.
Yeah. Yeah, we were working on that last class. Thank you so much.
Sure.
Yeah, working through the problems really helps.
Not a problem.
So it's the same time every week?
Yes.